SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Start करना. I'm Professor V.R. Trivedi, ex-professor and head Department of Mathematics, Bhavan Science College. Today we'll discuss determinant and its properties and applications. The great contributors in the theory of determinants and associated matrix theory are James Sylvester, Gabriel Cramer, who was just 18 years old when he was awarded a doctorate, Alexander van der Monde, who pursued his first career as a violinist before turning to mathematical research and teaching. He was one of the first to study determinants as a worthwhile subject in itself. Arthur Cayley, creator of matrix theory, William Hamilton, Laplace, and so on and so forth. In his address, the great mathematicians James Joseph Sylvester addressed, mathematics is not a book confined within a cover and bound between brazen clasps whose contents it needs only patience to ransack. It is not a mine whose treasures may take long to reduce into possession, but which fill only a limited number of veins and loads. It is not a soil whose fertility can be exhausted by the yield of successive harvests. It is not a continent or an ocean whose area can be mapped out and its contour defined. It is limitless as that space which it finds too narrow for its aspirations. Its possibilities are as infinite as the worlds which are forever crowding in and multiplying upon astronomers' gaze. It is incapable of being restricted within assigned boundaries or being reduced to definition of permanent validity as the consciousness, the life which seems to slumber in each molar, in every atom of matter, in each leaf and bud and cell, and is forever ready to burst forth into new forms of vegetables and animal existence. Now, my friend will introduce determinants and its properties.
My name is Devendra and I'll take the subject here forth, and in between I'll invite Professor V.R. Trivedi to give his special comments on determinants. So we are going to discuss about properties. Initially we start with the introduction part of determinants. Matrix, I think the name is clear to most of the viewers that are on show now. But we are going to see some strange properties of matrices. As in case of numbers, when we multiply two numbers, normally we see that 5 into 7, that is 35, and if we interchange the order of the numbers, that is 7 into 5, then also the answer does not change. So 35, 7 into 5, 35 is 5 into 7, but that does not happen here with matrices. So suppose I take two matrices A and B. In that case, AB may be giving us some other answer and BA might not give the same answer. So such special types of properties, we call them as strange properties. Matrix behaves very strangely. So let us see some of these properties. First of all, we talk about non-commutative nature of matrix multiplication and its zero divisor property. It's well known that matrix multiplication is not commutative. We see some counterexample on the screen. Let us take matrix A, 2 by 2 matrix 1 2 0 0, matrix B 1 0 3 0. Now when in this matrix, when you multiply A with B, taken A on the left and B on the right, the answer, it's clear that 7 0 0 0 is the answer. Whereas when you change the order of the matrix, you multiply B with A, then the matrix answer also changes. Multiplication answer becomes 1 2 3 6. So it's clear that AB is not equal to BA. So that means we can definitely say that matrix multiplication may not be always commutative. In given circumstances, it might become commutative, but not always. So this is one property, that matrix multiplication is not commutative. Similarly, when we talk about two numbers giving us answer 0, suppose A into B, I am talking about numbers, not on the screen, I am talking about the numbers A and B. A and B are real numbers, and suppose A into B turns out to be 0. In that case, we definitely can say one of them must be 0, because if both numbers A and B are non-zero, the product can never be 0. But that again does not happen with matrices. So we take two matrices A and B, and suppose the outcome of the product of matrix multiplication is a 0 matrix as shown, then in that case matrix A and B both might not be 0. We see a counter example here on the screen. Let us take matrix A to be 0 1 0 0 and matrix B as 1 0 0 0. So matrix A is not 0 because one of the entries in A matrix is non-zero, and similarly B is also non-zero matrix because in B also there is one entry which is non-zero. But when you multiply A with B, it can be seen that all the entries turn out to be 0. So AB becomes a 0 matrix. So that then this basically says that when A into B, matrix multiplication A into B is 0, does not necessarily imply that A is 0 or B is 0. Both can be non-zero. Let us similarly see something else. One more property similar. If the product of A with B, matrix A with matrix B is 0 matrix, that again does not mean reverse order multiplication BA is also 0. So the statement is when AB is 0, then BA may not be equal to 0. Again, there is a counter example on the screen for that. We take matrix A and B. A is 0 1 0 0, B is 1 0 0 0, and when you multiply both ways, AB turns out to be 0 matrix, but BA is not a 0 matrix. So we cannot say this also. That means AB is not only different from BA, but also even if AB is 0, does not mean BA is a 0 matrix. Suppose AB into AB two times is a 0 matrix. Does it actually follow BA is also 0? Again, we have a counter example here for the given matrix on the screen, matrix A and matrix B. You can see the matrix AB is having just one entry which is non-zero, and thereafter when you see AB square, that is AB, all the entries turn out to be 0. So AB is 0 for the given matrix. But now when we talk about BA, first we get BA has two entries which are non-zero at some other location, and BA square has just one entry which is non-zero. So again here we see that for given matrix A and B, AB is 0 matrix, but BA is not equal to 0. So the answer for the above question, does it follow that BA is 0? The answer is obviously no. However, it is worth noting that the counter example that we gave was a 3 by 3 matrix, but instead of that, if we take a 2 by 2 matrix, we will not be able to find a counter example satisfying the previous assertion. So if we take 2 by 2 matrix, actually one can show that whenever AB is 0, BA will also turn out to be 0. And I don't furnish the proof here. Proof is left to the viewer, so you can try. And one more thing, the counter example that we gave for the assertion that we just made had matrices A and B which satisfied a special property, that was A cube is 0 matrix and B cube is also 0 matrix. Suppose we don't take such a matrix, we don't take a matrix satisfying this criteria, we will not get the counter example for the previous assertion. Thus, from all this we definitely can say matrix multiplication, this operation matrix multiplication, behaves very, very strangely. However, if it is a case of determinant, then the product of A and B, take a determinant of product of two matrices is 0, does imply one of the matrix must have determinant 0. AB determinant is 0 implies either determinant A is 0 or determinant B is 0, hence BA determinant will also turn out to be 0. This can be seen, details are not done here, they are left to the viewers. So now therefore let us study determinants in detail. Some other properties of determinants we are going to see hereafter. So let us see the other property. We are going to talk about area, and we will relate the concept of area with determinants. So for that, let us understand the geometrical construction first of all. And for that, you can see on the screen, we have drawn a parallelogram. Actually, we have considered from the origin to P, we have considered a vector OP. We give it a name x vector. OP vector is a x vector. Similarly, another vector from origin towards R, we call it y vector. So there are two vectors. Using these two vectors, I have completed a parallelogram here. And you can see certain other things also on the screen. There is a perpendicular drawn from R on OP. It touches OP at G. So RG is a perpendicular on OP, and we take the direction of RG as G to R, and that vector we call as Z vector. Obviously the diagonal vector will be sum of x and y, so x plus y vector, that is OQ vector, and accordingly we can put down the coordinates. Suppose let the angle between these two vectors x and y is theta. In the positive direction it is measured anticlockwise. So theta is the angle between vector x and vector y. Now our aim is to compute the area of this parallelogram that you just saw on the screen, parallelogram OPQR. OPQR. Basically area of a parallelogram is base into height, but we will talk about determinants here, concept of determinant, and will show that determinant is very useful in getting the area also. So for that, let Z be the vector orthogonal to the projection of y on x, and theta be the angle between x and y. So using the concept of inner product, one can easily write cos theta is inner product of xy divided by norm x into norm y. It is easy to see from the figure that Z is y minus x upon mod x into mod y cos theta. This can be seen from the figure. From in the figure one can see that there is a right triangle ORG. Direction should be considered here. So there is a right triangle ORG, and if we talk about triangle of vectors, then see the direction of x is from O towards P, vector x, vector y is from O towards R, and vector z is G to R. So using the direction concept, we can say that the vector y can be written as z minus vector OG, and that using inner product can be written as seen in the equation here. Z is y minus x upon mod x mod y cos theta, and then we can put the value of cos theta and do some cancellation, and we finally get z equal to y minus some inner product, as you can see on the screen, into the direction vector x upon norm x unit vector. Sir will give some special comments here.
See here, while calculating this vector is y and this angle is theta, when you project this on this vector, here unit vector is x upon its length, x upon modulus x or norm x. So here this is the directions, and now this one is z. Now y equal to this angle between this theta, so cos theta is here y and x upon this one, and you have to take the unit vector. So this is same as yx norm x norm y. So this is cos theta. Now here when you take its projection in this direction, it will be y cos theta. y cos theta. So length will be this one. Now z is this one. So in order to get this, we have to change the direction. So that will be, z will be y minus y. ये positive है, ये negative directions है. So that will be x, y, then x upon modulus x or norm x, and that also here. So that will be y minus x upon norm x square. So that you can see on the screen also. So this one, so we have, if we call this P, then y is P plus Z. Okay. Now if you calculate the area just as shown by this one, if you calculate area A, that is base into height, and that gives, when you take this one, so this get cancelled, and here we have used this fact that y is z is y minus x upon